The warehouse stood in the Ardennes forest, temporary and cold, its corrugated metal walls doing little to keep out the December wind of 1944. Inside, under harsh electric lamps strung from the rafters, 5 German engineers gathered around something that should not have existed according to their understanding of armoured warfare. The vehicle before them was an American M36 tank destroyer, captured intact 3 days earlier near the Belgian town of Bastogne. Its turret still bore scorch marks from a Panzerfaust that had disabled its traverse mechanism but left the gun operational. The engineers had come from the Waffenamt testing facility at Kummersdorf, summoned urgently to examine this machine, whose presence on the battlefield represented something profoundly troubling. The chief engineer, a man named Hauptmann Klaus Richter, who had spent 15 years designing anti-tank guns for Krupp, approached the vehicle slowly. He had read the field reports. An American tank destroyer mounting a 90mm gun. The reports claimed it had destroyed a Panther at 2,000 meters, punching through the frontal armor. Another report described a King Tiger disabled from the side at 1,500 meters. These claims seemed impossible. The Americans had fielded 76mm guns on their Sherman tanks, adequate weapons, but nothing exceptional. The British 17-pounder was formidable, yes, but it fired a 3-inch projectile. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. A 90mm gun suggested something different entirely. That was the caliber of German anti-aircraft weapons, the famous 8,8 that had been adapted for anti-tank use. But those were static defensive weapons, not something you mounted on a mobile chassis and drove into combat. Richter circled the M36, taking measurements, making notes in a leather-bound journal. The vehicle was surprisingly compact for something carrying such a large gun. It was built on a modified Sherman chassis, recognizable by the track configuration and hull design, but the turret was entirely new, open-topped, providing no overhead protection but allowing for a larger gun and more efficient crew operation. The armor was thin, perhaps 38mm on the turret face, maybe 50mm on the hull front. This was a tank destroyer in the American style, built for speed and firepower rather than protection. But it was the gun that demanded attention. The barrel measured 14 feet from breech to muzzle, a length that spoke to high velocity and extreme penetrating power. Richter knew the physics. A longer barrel meant more time for propellant gases to accelerate the projectile, which meant higher muzzle velocity, which meant greater kinetic energy on impact, which meant deeper penetration of armor plate. He had designed guns in himself. He understood the mathematics. And looking at this barrel, doing calculations in his head based on caliber and length, he arrived at velocities that seemed absurd. If the Americans had developed propellants and projectiles to match this barrel length, they had created something that could defeat any German tank in service. The other engineers were examining the ammunition storage. They had found several rounds still in the racks, including what appeared to be armor-piercing projectiles of unfamiliar design. One engineer, a metallurgist named Dr. Werner Schmidt, was weighing a projectile carefully, measuring its dimensions, calculating its density. High-density tungsten core, almost certainly. The Americans had access to tungsten in quantities Germany could no longer obtain. The implications were troubling on multiple levels, tactical and strategic both. To understand why these engineers reacted with such concern, you must understand what German armoured doctrine had become by late 1944. The principles that had guided German tank design had evolved considerably from the early war years, when speed and mobility were paramount. The Panzer III and early Panzer IV models had emphasized maneuverability, adequate guns, and armor sufficient to resist the anti-tank weapons of 1939 and 1940. But 4 years of brutal combat on the Eastern Front against Soviet armor had changed everything. The appearance of the Soviet T-34 inches, 1941, had been a profound shock to German military planners. Here was a tank that combined sloped armor for maximum effective thickness, a powerful 76mm gun, wide tracks for mobility in mud and snow, and a diesel engine for reliability and reduced fire risk. German tanks of the period were outmatched in nearly every category. The Panzer III's 50mm gun could not reliably penetrate the T-34's armour at combat ranges. The vertical armour plates on German tanks offered no deflection advantage. The narrow tracks limited mobility in the conditions where the Eastern Front was fought. The German response had been to escalate armour thickness and gun calibre dramatically. The Panzer IV received a long-barreled 75mm gun and additional armour plates welded to the hull and turret. The new Panther tank, introduced in 1943 after the disaster at Kursk, mounted an even more powerful gun, the legendary 75mm Quapka 42, with its extremely high velocity and excellent armour penetration. The Panther's frontal armour was 80mm thick and sloped at 55 degrees, providing effective protection equivalent to perhaps 140mm against direct fire. The sides were 50mm, the turret front 100mm. But the ultimate expression of German armour philosophy was the Tiger II, called the King Tiger by Allied forces. This massive vehicle, weighing nearly 70 tons, mounted an 88mm gun derived from anti-aircraft weapons and carried armour that seemed almost absurd in its thickness. The frontal hull armour was 150mm thick, sloped at 50 degrees. The turret front was 180mm. Even the sides were 80mm. This was a tank designed to be invulnerable from the front and resistant even to flank shots at normal combat ranges. German engineers had convinced themselves they had solved the armour problem through sheer thickness. If you made the armour thick enough, if you sloped it properly, if you used face-hardened steel properly heat-treated, no gun could penetrate it at combat ranges. The Tiger II's frontal armour was considered effectively immune to every Allied tank gun in service as of mid-1944. American 76mm guns could not penetrate it. British 17-pounders struggled against it, except at very close range with special ammunition. Soviet 85mm guns required point-blank shots with perfect angle to have any chance. This invulnerability bred confidence that bordered on arrogance. Tank crews in Panthers and Tigers believed their frontal armour made them nearly unkillable in tank versus tank combat. Tactical doctrine emphasized frontal engagements where German armour superiority would decide the outcome. Manuals instructed crews to present the frontal aspect to enemy fire whenever possible, to use the armour as an active defence, while the superior German guns destroyed Allied tanks at ranges where return fire was ineffective. The mathematics seemed to support this confidence. A Panther's gun could penetrate a Sherman's frontal armour at 2,000 metres. A Sherman's 76mm gun could not reliably penetrate a Panther's frontal armour even at 500 metres. The Tiger II was even more dominant, essentially immune frontally while carrying a gun that could destroy any Allied tank at extreme range. But this confidence existed within a larger context that German engineers understood even if tank crews in the field did not. Germany, in late 1944, was a nation under immense industrial strain. The material situation that had allowed the Reich to build these massive tanks was deteriorating rapidly. Allied strategic bombing had begun disrupting production seriously. The loss of territories in the east had cut off access to critical resources. The naval blockade meant no imports of materials Germany lacked domestically. Tank production numbers told the story clearly. Germany produced approximately 6,000 Panthers during the entire production run from 1943 to 1945. Tiger II production reached only 489 vehicles total. These were not large numbers. Germany was building perhaps 100 to 150 tanks per month across all types by late 1944, and that production was declining, as factories were bombed and raw materials became scarce. The Americans, by contrast, were building tanks in quantities that German intelligence analysts struggled to believe. Reports indicated Sherman production alone exceeded 2,000 tanks per month at peak capacity. The United States had built over 49,000 Shermans by the time production ended. Even accounting for losses in combat and to mechanical failure, this meant American armoured divisions could replace destroyed tanks faster than Germany could build new ones. A German panzer division that lost 20 tanks in a week of heavy combat might wait months for replacements. An American armored division that lost 20 Shermans would have them replaced within days, sometimes within hours, as replacement vehicles were brought forward from depots. But quantity was not the only advantage the Americans possessed. They also had access to materials Germany lacked. Tungsten, critical for armor-piercing projectiles, came primarily from China and Portugal. Germany's access to both sources had been cut off. American tungsten supplies from domestic mines and South American sources were abundant. Molybdenum, used in armor steel alloys to improve hardness and resistance to penetration, came from mines in Colorado and Chile. Germany had limited domestic sources. High-grade steel production required manganese, chromium, nickel, and other alloying elements. Germany's supplies of all these materials were constrained and declining. The result was that German armor plate quality was deteriorating as the war progressed. Late-war Panthers had thinner armor than early models, and the steel was not properly heat-treated because the necessary furnaces and time were unavailable. Weld quality suffered as experienced workers were drafted and replaced with forced labor. Mechanical reliability declined as precision parts were replaced with cruder substitutes. A Panther built in 1945 was not the same quality as one built in 1943, though it looked similar from the outside. German engineers at facilities like Kummersdorf knew all of this. They understood that the massive tanks Germany was building were becoming increasingly difficult to produce and support. The King Tiger's 70-ton weight meant it could not cross most bridges. Its fuel consumption was enormous, reaching perhaps 120 litres per 100 kilometres off-road. Germany was already experiencing fuel shortages that grounded Luftwaffe squadrons and left tank divisions immobilized for lack of gasoline. A Tiger II battalion required dedicated fuel trucks and supply trains that were increasingly vulnerable to Allied air attack. The vehicle the German engineers were examining had not appeared by accident. The M36 tank destroyer represented a specific American response to intelligence reports about German armor developments. American ordnance officers had known since 1943 that German tanks were becoming heavier and better protected. Reports from North Africa described the Tiger I with its 88mm gun and thick armor. Intelligence from Italy confirmed the Panther's introduction with its sloped armor and powerful gun. American tank crews were encountering these vehicles and discovering that their existing weapons were inadequate. The M10 tank destroyer, mounting a 3-inch gun equivalent to 76mm, could penetrate a Panther's side armor but struggled against frontal plates. The M4 Sherman with the 76mm gun faced similar limitations. American ordnance committees recognized they needed more penetrating power, and they needed it quickly as the invasion of France approached. The solution was to adapt an existing anti-aircraft weapon, the 90mm M1 gun, for anti-tank use. The 90mm M1 had been designed in the late 1930s as a high-altitude anti-aircraft weapon. It fired a 24-pound projectile at high velocity to reach bombers flying at 30,000 feet. The ballistics were already proven. What engineers at Aberdeen Proving Ground needed to do was modify the weapon for tank use, which meant redesigning the recoil system, adapting the breech for easier loading in a confined space, and developing armor-piercing ammunition specifically for anti-tank work. The resulting weapon was designated the 90mm M3 gun. Its barrel measured 14 feet 7 inches long, giving a length-to-caliber ratio of 49.5. This was an extremely long barrel by the standards of 1944, comparable to the German 88mm Quar 43 mounted on the King Tiger. The long barrel meant high muzzle velocity. With standard M77 armor-piercing ammunition, the 90mm M3 achieved a muzzle velocity of 2,800 feet per second. With the newer hypervelocity armor-piercing ammunition using tungsten cores, designated M304, velocity reached 2,960 feet per second. The penetration values were remarkable. At 1,000 yards, the M77 armor-piercing shot could penetrate approximately 7 inches of vertical armor plate. That was 178mm, enough to defeat the frontal armor of a Panther, which had 80mm of actual thickness, providing about 140 millimeters of effective protection due to slope. At 500 yards, penetration increased to nearly 8 inches, or 203 millimeters. The hypervelocity M304 round was even more powerful, capable of penetrating over 7.5 inches at 1,000 yards under test conditions. These figures were not theoretical. They had been verified at Ardennes Proving Ground through actual firing tests against armor plate of known thickness and hardness. American testing protocols were rigorous. Plates were set at various angles. Projectiles were fired at measured velocities. Penetration was defined as complete perforation, where the projectile passed entirely through the plate or caused spalling on the rear surface, severe enough to injure crew members. The results were documented in technical reports with photographs showing the damage. The M36 tank destroyer was designed around this gun. Engineers at Fisher Tank Division used the M10A1 hull as the basis, which itself was derived from the Sherman chassis. The hull armor remained modest, just 2 inches on the frontal plate and 1.5 inches on the sides. This was adequate against small arms fire and shell fragments, but offered no protection against German tank guns. The philosophy was the same as all American tank destroyers: mobility and firepower rather than protection. The crew would avoid being hit rather than relying on armor to absorb hits. The turret was new, larger than the M10s to accommodate the bigger gun and its recoil system. It was open-topped, which reduced weight and allowed fumes from firing to escape quickly. 5 men crewed the vehicle: a commander, gunner, loader, driver, and assistant driver, who also operated a bow machine gun. The commander and gunner shared the turret with the loader, while the driver and assistant driver sat in the hull. Radio equipment was standard, allowing communication with other vehicles and with forward observers who could direct fire onto targets beyond the crew's direct vision. Production began in June of 1944 at facilities including Fisher Tank Division and Massey Harris. The urgency was considerable. Allied forces would be invading France within weeks, and intelligence suggested they would face significant numbers of Panthers and Tigers. The first M36S reached Europe in September of 1944, with the 776th Tank Destroyer Battalion receiving the initial allocation. Additional battalions were re-equipped through the fall as production increased. By December, when the Germans launched their Ardennes offensive, several American tank destroyer battalions were operating M36S in Belgium and eastern France. These units were organized differently from tank battalions. They were meant to be mobile, held in reserve, and committed to threatened sectors where German armor appeared. Doctrine emphasized using the terrain, engaging from concealed positions, firing and displacing before German tanks could return effective fire. The M36's high-velocity gun meant it could engage at ranges where German tanks might not even see the tank destroyer's position. The M36's combat debut was not dramatic or well documented in the way major battles are recorded. Tank destroyers engaged German armor in small unit actions, often at considerable distance, sometimes in conditions where positive identification of targets was difficult. But reports began accumulating through October and November of 1944. An M36 of the 654th Tank Destroyer Battalion engaged a Panther near Nancy, France, destroying it with a single shot at approximately 1,800 meters. The crew reported the round struck the turret face and penetrated completely, causing catastrophic internal damage. The Panther burned. Another engagement near Metz involved M36S engaging dug-in Panthers that were providing anti-tank support for German infantry. The Panthers were hull down, presenting minimal targets with just turrets exposed. American tank destroyer crews engaged methodically, using high-explosive rounds to suppress German infantry while waiting for clear shots at the armor. When opportunities came, armor-piercing rounds were fired. 2 Panthers were confirmed destroyed, one burning after a turret hit, another immobilized with a round that penetrated the gun mantlet and disabled the weapon. These engagements established a pattern. The M36's gun could defeat Panthers frontally, at ranges where Panther guns were equally dangerous. This was different from the earlier situation where Shermans and M10 tank destroyers needed to flank Panthers or wait for close-range shots. The 90mm gun changed the mathematics of engagement, giving American crews a weapon that matched or exceeded German tank guns in penetration. The physics involved were straightforward but unforgiving. When an armor-piercing projectile strikes armor plate, the outcome depends on several factors. The projectile's kinetic energy, its hardness relative to the armor's hardness, the angle of impact, and the armor's thickness and quality. Kinetic energy is the critical variable, determined by the projectile's mass and velocity. The formula is 1/2 mass times velocity squared, which means velocity matters enormously because it's squared in the calculation. The 90mm M37 armor-piercing shot weighed 24 pounds. Travelling at 2,800 feet per second, it carried tremendous energy. When this projectile struck armor, several things happened in microseconds. The hardened steel nose of the projectile contacted the face-hardened surface of the armor plate. If the projectile had sufficient energy and hardness, it would break through the hardened face layer and begin penetrating the tougher but softer core of the armor. The projectile would deform somewhat as it penetrated, mushrooming slightly, but if it maintained structural integrity, it would continue through the plate until it either perforated completely or expended all its energy. German armor was face-hardened, meaning the outer surface was extremely hard to shatter incoming projectiles, while the inner core was tougher and more resistant to cracking. This technique worked well against projectiles with moderate energy, but the 90mm round carried enough energy that the hardened face merely slowed it without stopping it. Once through the face layer, the projectile's mass and remaining velocity were sufficient to punch through the core and exit the rear of the plate. The effect inside a tank was catastrophic. The projectile itself, travelling at perhaps 1,000 to 1,500 feet per second after penetration, would strike anything in its path. Equipment would be smashed, ammunition could be detonated. Crew members hit directly would be killed instantly. But even if the projectile missed the crew, secondary effects were deadly. Spalling, where fragments of armor from the rear surface broke away and sprayed through the crew compartment, could wound or kill everyone inside. The shockwave from impact could damage vision equipment, fire control systems, and radios. Smoke and dust would fill the compartment, choking the crew and reducing visibility to zero. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German tank crews who survived hits from 90mm guns described the experience as overwhelming. The sound was described as a tremendous crack, like lightning striking metal. One Panther commander, who bailed out after his tank was hit near Bastogne, said the round came through the turret front, passed through the fighting compartment, missing the crew by inches, and exited through the rear plate. The noise and shock left him temporarily deaf. Smoke filled the turret instantly. He couldn't see, couldn't hear, and couldn't determine if his crew was wounded. Training took over. He ordered everyone out. They abandoned the tank, which was still mechanically functional but had a hole clean through it. Back in that cold warehouse in the Ardennes, Hauptmann Richter was reaching conclusions he did not want to accept. His team had spent hours examining the M36, measuring every aspect of the gun and ammunition, reviewing the ballistic tables they found in the vehicle's storage bins. American crews kept technical manuals and range cards in their vehicles, and this M36 had been captured so quickly the crew had no time to destroy documents. The Germans now had complete information about the weapon's capabilities. Dr. Schmidt had analysed the armour-piercing projectile in detail. He had measured its dimensions precisely. 90 millimetres in diameter, 354 millimetres long, weighing approximately 11 kilograms. The projectile body was hardened steel, properly heat-treated to maintain penetrating capability without shattering on impact. The driving band was copper, soft enough to engage the rifling without damaging the barrel. Most significantly, the projectile had a dense core, almost certainly tungsten carbide, that provided maximum penetration effect. Schmidt performed calculations based on the projectile's mass and the muzzle velocity indicated in the American documents. His figures matched what Richter had estimated. Kinetic energy sufficient to penetrate 180 millimeters of vertical armor at 1,000 meters. Against sloped armor, the effective penetration would be less, but even accounting for angle effects, the weapon could defeat a Panther's frontal armor at combat ranges. It could penetrate a Tiger II's side armor easily. Only the Tiger II's frontal armor, 150 millimeters sloped at 50 degrees, might resist the round at longer ranges, and even that was not certain. Another engineer, Lieutenant Hans Becker, was examining the gun's mounting and recoil system. He was impressed despite himself. The Americans had solved the problem of mounting a large, powerful gun on a relatively light chassis. The recoil system absorbed the tremendous forces generated when the gun fired, preventing damage to the vehicle and keeping the chassis stable enough for accurate follow-up shots. The turret traverse mechanism, though manually operated, was smooth and well designed. The gun could be laid on target quickly despite its size. The ammunition storage concerned them. The M36 carried 47 rounds of 90mm ammunition in 7 portatives, racks distributed around the hull and turret. This was not a large load compared to the 90 rounds a Panther carried for its 75mm gun, but it was adequate for the tank destroyer's intended role. More troubling was the variety of ammunition available. The documents listed armor-piercing, high-explosive, and smoke rounds as standard. They also referenced hyper-velocity armor-piercing ammunition with tungsten cores, though none of these special rounds were found in this particular vehicle. Richter drafted his report that evening, writing by lamplight in a requisitioned farmhouse. His assessment was bleak. The Americans had fielded a weapon system that could engage German heavy tanks on equal or superior terms. The M36's 90mm gun matched the penetrating power of the German 88mm Quak 36, mounted on the Tiger I, and approached the performance of the longer 88mm KUK 43 on the Tiger II. Unlike German assault guns and tank destroyers, which were built on obsolete chassis and produced in limited numbers, the M36 was built on the reliable Sherman chassis using proven components. American industrial capacity meant these vehicles could be produced in large quantities. The report noted specific concerns. The M36 was lighter and more mobile than German heavy tanks, giving it tactical flexibility. Its open turret was a vulnerability, but also reduced production time and allowed better crew efficiency. The gun's high velocity meant flat trajectory and excellent accuracy at range. The availability of tungsten-cored ammunition gave it penetration capability that exceeded even optimistic German estimates. Most critically, the M36's appearance suggested American ordnance development was keeping pace with or exceeding German developments, despite Germany's head start in heavy armor. Richter included recommendations. German tank crews needed to be informed about this threat. Tactical doctrine should emphasize engaging M36s at maximum range before they could close to distances where their gun was most effective. Panthers and Tigers should avoid presenting flank armor, even though the M36 could penetrate frontal armor as well. Ambush tactics and use of terrain were essential. But Richter knew these recommendations were inadequate. If American tank destroyers could penetrate German heavy armor frontally, then the entire premise of German armored superiority was questionable. The report went up through channels, reaching the Waffenamt headquarters in Berlin within days. Other reports from other engineers examining other captured M36s confirmed Richter's findings. By January of 1945, German High Command had to acknowledge that American forces possessed tank destroyers capable of defeating any German armor at typical combat ranges. This information was classified and distributed to panzer divisions, but the dissemination was limited. Many tank crews never received the intelligence, and those who did often dismissed it as pessimistic or exaggerated. The German offensive in the Ardennes, launched on December 16, 1944, was intended to split Allied armies and capture the port of Antwerp, cutting off supply lines and forcing a negotiated peace in the west. German planners committed their best remaining armoured divisions, including units equipped with King Tigers and Panthers. They believed their armor superiority would be decisive in the forested, hilly terrain where American forces were thinly spread. The offensive achieved initial surprise, pushing deep into American lines and creating chaos in the first days. But the Americans responded with their characteristic industrial abundance. Reinforcements poured into the threatened sectors. The 101st Airborne Division held Bastogne against encirclement. Tank destroyer battalions, including those equipped with M36s, were rushed to critical positions. By late December, as the German offensive lost momentum, American tank destroyers were engaging German armor across the entire front. The M36 proved its value repeatedly. On December 23rd, near Mannheim, an M36 from the 643rd Tank Destroyer Battalion engaged a King Tiger at approximately 1,300 meters. The German tank was moving along a road, presenting its frontal aspect. The American crew fired. The 90mm round struck the King Tiger's turret front, just beside the gun mantlet. The massive tank stopped abruptly. Smoke poured from hatches. The crew bailed out. When American forces examined the tank later, they found the armor-piercing round had penetrated the 180mm of turret armor, travelled through the fighting compartment, and lodged in the rear turret wall. The King Tiger, Germany's most heavily armoured tank, had been defeated frontally by a weapon the Germans had only recently discovered existed. Another engagement near Hotten involved M36s, engaging Panthers in a village. German tanks were supporting infantry, moving through streets where their mobility was constrained. American tank destroyers positioned on high ground engaged at ranges from 800 to 1,200 meters. 3 Panthers were destroyed in 15 minutes of firing. All 3 were hit frontally, with rounds penetrating the hull or turret and causing ammunition fires. The German crews had no answer. Their own guns could have penetrated the M36's thin armor easily, but they could not locate the American positions quickly enough to return effective fire before being destroyed. These engagements revealed something German tankers were increasingly forced to confront. The armor superiority they had relied on was no longer absolute. American weapons could defeat German heavy tanks frontally, at ranges where tactical advantage was minimal. The psychological effect was significant. Panther and Tiger crews, who had felt invulnerable when properly positioned, now understood they were vulnerable even in frontal engagements. The confidence that had characterized German armored operations in earlier years was eroding under the weight of material evidence. German tactical reports from January of 1945 reflected this new reality. Battalion commanders noted that American tank destroyers, equipped with large-caliber guns, were appearing in increasing numbers. They warned crews to avoid exposing themselves unnecessarily, to use terrain more carefully, and to engage at maximum range. But these warnings came too late to change the trajectory of the campaign. The Ardennes offensive failed. German armor losses were severe, with hundreds of Panthers and Tigers destroyed or abandoned. The Wehrmacht's armored reserve, rebuilt carefully over months, was shattered in weeks. For Hauptmann Richter and his fellow engineers, the failure in the Ardennes confirmed what their examination of the M36 had suggested. German armor, despite its technological sophistication and impressive protection, could not overcome American material superiority. The Americans had more tanks, more ammunition, more fuel, and increasingly, better weapons. The 90mm gun was not the only new threat. Intelligence reported that American forces were also deploying the T-26 heavy tank, mounting a 90mm gun in a fully enclosed turret with heavy armor. The British were upgrading their Shermans with 17-pounder guns that matched German penetration capability. The strategic situation was deteriorating on every front. In the east, Soviet forces were advancing through Poland toward Germany itself, equipped with improved T-34, 85 tanks, and heavy IS-2 tanks mounting 122mm guns. In the west, Allied armies had recovered from the Ardennes setback and were preparing to cross the Rhine. German production could not replace losses. Fuel shortages immobilized entire divisions. The Luftwaffe could no longer contest Allied air superiority. leaving German ground forces vulnerable to fighter bombers that destroyed tanks and supply columns with impunity. As 1945 progressed, M36 tank destroyers participated in every major American operation. They crossed the Rhine in March, engaged German armour in the Ruhr pocket, and advanced into central Germany. Combat reports documented their effectiveness consistently. Against dug-in Panthers and Tigers defending river crossings and fortified towns, the 90mm gun provided American forces with a weapon that could engage on equal terms. German tanks that would have required flanking maneuvers or air support to defeat with earlier American weapons could now be engaged frontally. The Battle of the Ruhr pocket in April demonstrated the extent to which German armoured power had declined. Entire panzer divisions were encircled and destroyed. Surviving German tankers abandoned their vehicles for lack of fuel or after minor mechanical failures they lacked parts to repair. American forces captured hundreds of Panthers and Tigers intact, simply parked beside roads or hidden in forests where their crews had walked away. The industrial war had been decided. Germany could no longer sustain its armoured forces in the field. Individual engagements in these final weeks showed how thoroughly the balance had shifted. Near Leipzig, an M36 engaged a King Tiger at close range in an urban environment. The German tank had taken position at an intersection, covering multiple approaches. American infantry could not advance without being destroyed. An M36 manoeuvred through side streets, approaching from an angle the German crew did not expect. At 300 meters, the tank destroyer fired 3 rounds in rapid succession. The first struck the King Tiger's side armour, 70 tons thick, and penetrated easily. The second struck the turret side. The third was unnecessary. The massive German tank was burning, its crew dead or dying inside. This engagement would have been unthinkable in 1943, when the King Tiger was being designed. German engineers had created a tank they believed was invincible, protected by armour so thick that no existing weapon could defeat it at combat ranges. But American ordnance development had not stopped. The 90mm gun represented a direct response to German armour evolution, and it had succeeded in creating a weapon that could defeat even the heaviest German tanks. By May of 1945, when Germany surrendered, M36 tank destroyers had proven themselves among the most effective American armoured vehicles of the war. Production totaled over 2,000 vehicles, far fewer than Sherman's but sufficient to equip multiple tank destroyer battalions. Combat losses were modest, partially because the M36 entered service relatively late in the war, but also because its gun allowed crews to engage German armour at ranges where return fire was less effective. Many M36s survived the war, served in other conflicts, including the Korean War, where they again provided mobile anti-tank firepower. For German engineers who survived the war, the M36 represented a lesson in the futility of trying to achieve technological superiority without the industrial base to sustain it. Germany had built remarkable tanks, well designed and powerfully armed. But these tanks existed in limited numbers, consumed resources Germany did not have, and ultimately could not decide the war's outcome because there were never enough of them, and the Allies could counter them with new weapons developed and produced in massive quantities. Hauptmann Richter survived the war. In later years, interviewed by historians studying German armour development, he described examining the captured M36 in December of 1944. He said he knew immediately upon seeing the 90mm gun that German armour superiority was over. The mathematics were clear. The Americans had fielded a weapon that could defeat any German tank, and they had done so using industrial methods that allowed mass production. Germany could not respond with equivalent weapons in equivalent numbers. The war was lost, though it would take months more of fighting before that reality was accepted officially. The story of Wehrmacht engineers examining a captured M36 and confronting the reality of its 90mm gun's penetration capability is more than a tale of technical surprise. It represents a microcosm of why Germany lost World War II. The Third Reich had challenged nations with far greater industrial capacity, larger populations, and access to more resources. German military planning had assumed that superior training, better tactics, and more advanced technology would compensate for these disadvantages. For a time, this assumption appeared valid. German forces achieved stunning victories from 1939 through 1942, but industrial warfare between modern nations is not decided by initial advantages or tactical brilliance alone. It is decided by the capacity to sustain military forces over years of combat, to replace losses, to adapt to enemy innovations, and to produce weapons and equipment in quantities sufficient to overwhelm opposition. The United States possessed this capacity to a degree unprecedented in history. American factories produced nearly 300,000 aircraft during the war, millions of vehicles, billions of rounds of ammunition, and quantities of every other military necessity that German planners found difficult to comprehend. The M36 tank destroyer was a single example of this industrial capacity applied to a specific military problem. American ordnance officers identified a need for greater anti-tank firepower. Engineers designed a solution using existing components where possible to accelerate development. Factories produced the new weapon in quantities sufficient to equip multiple battalions. The weapon reached combat units within months of the first prototype. This cycle of identification, development, production, and deployment happened repeatedly throughout the war, in every category of military equipment. German industry could not match this pace. Even when German engineers designed superior weapons, production was constrained by material shortages, bombing damage, and competing priorities. The King Tiger was an impressive tank, but Germany built fewer than 500 of them. The M36 was a capable tank destroyer, and America built over 2,000. The Sherman tank, despite its limitations against German heavy armor, was produced in numbers exceeding 49,000. Germany's total production of all tank types from 1939 to 1945 was approximately 25,000 vehicles, and this figure includes obsolete models and captured vehicles pressed into service. The Wehrmacht engineers examining that captured M36 in the Ardennes were confronting a truth Germans were forced to accept as the war progressed. Germany had initiated a conflict it could not win because the fundamental balance of industrial power was overwhelmingly against it. Courage, skill, and technological sophistication could not overcome disparity in production capacity measured in orders of magnitude. Every German tank destroyed required months to replace, if it could be replaced at all. Every American tank destroyed was replaced within days or weeks. This lesson extends beyond World War II. It speaks to the nature of modern warfare between industrialized nations, where victory depends not just on battlefield performance, but on the ability to sustain military operations indefinitely. Nations that cannot replace losses, that cannot adapt their industries to wartime production, that lack access to critical resources, will lose conflicts against opponents who possess these capabilities. This was true in the American Civil War, where the industrialized North overwhelmed the agricultural South. It was true in World War I, where the combined industrial capacity of the Allies eventually exhausted the Central Powers. It was true in World War II, where the Axis nations challenged opponents whose combined industrial output they could never match. For students of military history, the M36 tank destroyer and German reactions to it offer insights into how wars are actually won. Popular narratives often focus on dramatic battles, brilliant generals, and technological wonders. These factors matter, but they exist within a larger context of industrial capacity, resource availability, and sustainment capability. The side that can build more weapons, supply more ammunition, replace more losses, and maintain the fight longer will usually prevail, assuming some minimum level of tactical competence. The German engineers in that cold warehouse in December of 1944 were measuring more than armor penetration when they examined the M36. They were measuring the gap between what Germany needed and what Germany could produce. Between the war Germany thought it was fighting and the war it was actually losing. The 90mm gun that could penetrate 200mm of armor was not just a weapon. It was evidence of American industrial capacity applied to military problems, evidence that arrived too late for German forces to counter, evidence that made the final outcome inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.